So, hello again, everyone. Uh, I'm Francine Kisha de Mesa, and I'm here to discuss the laboratory activity number 8, which is the sampling and the aliasing under the digital signal processing. So, in this experiment laboratory, we explored how a continuous signal behaves when sampled at different rates and how aliasing occurs when the sampling frequency is too low. So the main goal of this activity is to understand the Nyquist-Shannon sampling theorem and see how it affects the accuracy of digital signal representation. So before diving into the code, let's briefly recall what sampling means. So sampling is the process of converting a continuous time signal as denoted as x of t into a discrete time signal, which is the time signal x of n, and the rate at which samples are taken per second is called the sampling frequency, which is represented as f sub s. Then, according to the Nyquist-Shannon sampling theorem, for perfect signal reconstruction, the sampling rate must be at least twice the maximum frequency of the signal. So, this is written as f sub s is greater than or equal 2 times f sub max, or in equation form, this one right here. And if this condition is not met, aliasing occurs, which means that the high frequency components of the signal are misinterpreted as lower frequencies. So, as a result, the reconstructed signals will look distorted or incorrect. So let us move on to the code. So right here, in the first part, this should be lab 8. So again, we import the libraries, the NumPy and the Matplotlib. Then we create or define the continuous time signal parameters, is the sine wave with the frequency of 5 hertz. So it means it completes 5 cycles per second. So here, f signals equals to 5 hertz. The variable t is generated using the NumPy's line space, which creates a 1,000 space points between 0 and 1 seconds. Then the x equals NumPy sine of 2 times pi times f sub signal times t. This produces a smooth sine wave, which is our reference continuous signal. So for the first sampling condition, we use sampling frequency of this one, the 50 hertz. Let's move on here to the second part, which is the second activity. So yeah, we use a sampling frequency of 50 hertz, which is much higher than twice our signal frequency. So here, in fs high is 50, since 50 is greater than 2 times 5, it satisfies the Nyquist rate. And the array, n high represents discrete time points from 0 to 1 in steps of 1 over 50, or this one, which is the fs high. Then in the x high, this generates the corresponding sampled amplitude. So this is called proper sampling. The samples are accurately represented, the true sine wave without distortion. So in the next part, right here, the third rather, we simulate the undersampling by setting the sampling frequency to 6. So this one, f is low. which is fs low is equals to 6, which is less than twice the signal because it violates the Nyquist condition. The sampled points will not represent real frequency correctly, which leads to aliasing, where the sampled signal appears to have a lower frequency than the original. So here, then let us move. Here in the sampling, just like here in the second one, which is the N high, here is the N low in this part. Let's show here the results, the visual output of the code. First is the continuous time signal, which is shown here in this blue line. So this represents the original analog sine wave. Then next is with low right here, I'm sorry, in this part this should be 50 hertz and not 5 hertz. So in this part then we have here the low sampling frequency in the 6 hertz, which is the aliasing. So in this part, the green stem points appear irregular form and form pattern that looks lower in the true frequency. So this is aliasing. The high frequency waveform now appears to oscillate more slowly even though the actual signal hasn't changed. So in reality, the signal's energy was folded back into lower frequency band because the sampling rate was too low. My screen is kind of glitching. Let us now move to the guide questions. What condition must be satisfied to prevent aliasing according to the Nyquist theorem? So, as mentioned earlier, the sampling frequency must be greater than twice the highest frequency component of the signal to accurately capture all details and to avoid distortion. Next, what happens when the sampling rate is exactly equal to twice the signal frequency? So, when sampling rate equals twice the signal frequency, the samples may form a repetitive or constant pattern, making it hard to distinguish the signal's actual shape or phase. Lastly, explain why the aliased signal appears to have a lower frequency than the original. So, aliasing folds higher frequencies back into the lower frequency range when sampling rate is too low, making the signal appear slower or lower in frequency than it really is. Then lastly, give real-world examples where aliasing is a problem, like audio recording and video. So in audio recording, aliasing can cause unwanted tones or distortions that degrade the sound quality and in videos, it can produce flickering effects or stripe patterns, especially when filming fast motion or detailed textures. So, just like what happened earlier when I was recording this recording my screen, I think that's an example of aliasing. So, yes. So, that is all for the laboratory 8. And